Remember in slope-intercept form, y equals mx plus b, one of the reasons that that was a goal to write that type of equation was because it told you the slope, if it was going up to the right or down to the right, if it was steep or gentle, and where across the y-axis. For a straight line, which is pretty simple, and a linear pattern, that's really most of all what you need. You didn't have the x-intercept, that was about it, but it was just a couple steps away to find the x-intercept. Quadratic patterns are a lot more complicated. They've got symmetry, they curve, they have up to 3 intercepts, 2x's and a y-intercept. We'll be looking at more of those with these investigations. But they've also got which way they open, if they're skinny or wide opening, they call that vertically stretched or compressed, if they open up or if they open down. And so there's a lot going on with quadratic patterns, and unfortunately, there is no one form of a quadratic function that tells us all of those important pieces of information. So there's one form that tells us where the vertex is. There's one form that tells us where the x-intercepts are. There's one form that tells us what what if it opens up or down, if it's wide or skinny, and where the y-intercept is. So you can have like one or two pieces of information, but none of the others. But if you can change forms from one form to another, then you can calculate each of those pieces. And we're going to look at those processes and why each form tells us what it does about the shape of a parabola. And also remember, in the real world, you usually have your data. You maybe know that it's a quadratic pattern, but you're trying to write the equation to fit that data. The type of data you have is going to determine which form of a quadratic equation you're going to try to write. If you have x-intercepts, you're going to go to factored form. If you have the vertex, you're going to go to vertex form, which we're not going to spend time on this year because of just time constraints, and it's a pretty complex, very difficult to teach through remote learning like we are. And then if you have the y-intercept in the shape of it, opening up or down, then you could use what's called the standard form. And that's so the type of data might determine which form you're trying to fit it into, and then you take the form that you wrote, convert it to one of the other forms, and you get other information that you might have been missing. So that skill of being able to change from one form to another is really important, and being able to connect the components of a parabola and the pattern and the pieces of that scenario to the equation. Because remember, these pieces, intercepts, vertex, and the shape of the curve are all really important pieces of information for the scenario. When we were talking about the optimization problem, that cookies for COVID, we were looking for the high point. That's the vertex. We weren't really interested in the x-intercepts or even the y-intercept because they didn't entirely make realistic sense. They weren't very helpful. If you were looking at something like a projectile moving through the air, you're going to use standard form because the force of gravity and the initial velocity and things like that, those are going to be really important pieces in that type of a problem. So it just depends. So let's look at the first 3 prompts in part A where it talks about A, B, and C. A and C you've already looked at in ax squared plus C in the previous set of investigations. So let's just do a review of that though. So remember the A value, that's kind of like the slope of a quadratic pattern. It determines how wide or skinny the parabola is, if it opens up or if it opens down. So when A gets bigger, greater than 1, it gets skinnier. We call that vertical stretching. Imagine the two ends of that thing are being pulled upwards, like two pieces of a bungee cord. When it gets smaller, between 1 and 0, it makes that parabola very flat. We call that vertical compressing. So it's like you're pulling down on the two sides of the parabola, pulling it down towards the x-axis. It flattens it out, it vertically compresses it. And if A is negative, it opens downwards. Those same patterns regarding the vertical stretching and compressing hold true. Okay, so let's recap that in our notes. So we have the A value. So when A is greater than 1, so think of it as increasing, we call that vertical stretching. When A is between 0 and 1, that is vertical compressing. And when A is positive, opens up. When A is negative, it opens down. And as a little recap of why that works, that's why I have this image over here. So notice the red line is just plain old y equals x squared, so a is 1. As that a value gets bigger, imagine you're just looking at this one point on the parabola. The same thing happens to all the points on each parabola, but if instead of having a equals 1, a equals 2, that's going to make the y value, the value of that term, twice as big, so it stretches it upwards. It does the same thing on the other side. So see how we call it vertical stretching, because it's like it's taking all of the y values that it would have had if y equals x squared, and it's stretching them upwards. So if y equals 3x squared, it would stretch it upwards even more. And then if it's less than 1, for example, if a was 1/2, it would take that same y value and x is 1 and cut it in half. And it would do that to all the points along that curve, and the entire parabola would be stretched downwards. So you can kind of think of the a value as the slope, and the c value is your y-intercept. And again, we're just going to, even though we looked at this before, we're just going to do a review of why that is. So the c value is the y-intercept. It vertically shifts the parabola up and down without changing its shape. It's not multiplied by x or anything like that. It just moves it up and down. And the value of c is equal to the value of the y-intercept, where it crosses the y-axis in this case. Now we're going to look at what happens when our parabola isn't centered on the y-axis, so don't get used to thinking of the c value as being where the vertex is on the y-axis. It's just where the line crosses the y-axis, because not all parabolas we're going to find are centered on the y-axis, but the c value is always the y-intercept. So c equals the y-intercept, which is the value of y when x is 0. And it's the y-intercept for the same reason the b value in y equals mx plus b is the y-intercept for a linear function. So if you were to take your y equals ax squared plus bx plus c, and you put in x equals 0, you would have y equals a times 0 squared plus b times 0 plus c. And anything times 0 is 0. And so if x is 0, the term that you're left with in this form, y, is equal to whatever is there. That's not affected by x being 0 because it's not multiplied by x. You're left with y equals c. So that's your y-intercept. Not always the vertex. It is sometimes the vertex when you don't have this bugger of a b value, which kind of complicates things. So this is what we'll talk about next. And notice what I said, this one's a bit more difficult to understand, so don't worry too much about it now. So going back to that manipulative, I'm going to set my c back to 0. So this one's just sitting right there. I'm not going to worry about the a value. So watch what happens, and hopefully you've done this, when you change the b value. So I'm going to increase the b value. At first, it looks like it shifts the parabola to the left, but then it starts going down. Notice the y-intercept isn't changing. The shape of the parabola isn't changing. It's not making it wider or skinnier or flipping it over anything. It's just moving it down to the left. Notice the value of b does not indicate like the horizontal shift of the vertex. So like if I have a b value of 5, my vertex hasn't shifted over 5 units. It's also not the value of this other x-intercept. Notice b is 5, but it's crossing the x-axis here at negative 3.3. So it's not a specific point on your parabola. If I move it the other way, the exact opposite happens. So it moves to the right and down, keeping its same shape. Remember, if my c value in this case is 0, that still means that it has to go through 0 when x is 0. Okay, so it still has the same y-intercept. It's just changing where the vertex is. So all we're going to take away from this for now, for this year, because we're in this remote learning mode, is just suffice to say that the b that is not 0. So if it is greater than or less than 0, so it's not just 0, you have ax squared plus c. If you actually have a bx term, there indicates that the parabola is not centered on the y-axis. It moves it off of the y-axis. The vertex isn't on the y-axis. It is somewhere moved off to the side. So b value that is not 0 indicates the parabola is not centered on the y-axis. It's horizontally and vertically shifted. But the direction that it goes and everything is a little bit fickle to follow. So we're not going to write a hard rule for that. But just suffice to say, if you have ax squared plus bx plus c, there's a bx term, it's no longer centered on the y-axis.